Hello, hello. It was a Jalen sighting. Oh, I'm not trying to pry, but that was a Jalen sighting. Okay, hello, Jalen. Hello. Wait, sorry. Okay, I shouldn't do that. I know. I take it back. I'm just excited when I meet you guys, blah, blah, blah. Hold on. All right. So I'm saying hello, hello, hello. Uh, Hello. Yes. So hello. Good afternoon, Olsmail. Good afternoon, David Khan. Good afternoon, Diana. Hi, Sarah. Good afternoon, Long. Oh, yes. Yes, long time no see. Thank you for remembering. Yes, long time no see. That's a good point. Good afternoon, Amy K. Good afternoon, Jay Lynn. Sorry to call you out twice now, 3 times. Good afternoon, but it's good to see you. Good afternoon, Chloe. Good afternoon, Ashley, whose name I will never forget. Good afternoon, Brooke, whose name I will never forget. Top of the afternoon, Abdel. Good afternoon, Samuel, Book Koyaso. Good afternoon, Jasmine. Good afternoon, Shakia. Good afternoon, Brianna, whose name I will never forget. That's true of all of you, of course, except that I will forget. Okay, you get it. All right. So hello, everybody. All right, we're gonna start. We are a new homework was posted. I'm just going to say this quickly. A new homework was posted. It was posted for this Wednesday, which is a little shorter than usual, but it's a short homework. If you get what's now starting to be going on, if you get the conclusion that I came to with the last class, I think the last real class, maybe it was the last video class. I'm not, anyway, if you're starting to follow or you are following what's going on with this cosine solution to the differential equation, then you will find homework 3 a lot shorter than homework 2, a lot shorter than homework 2. It's not a trick. Like if you don't get what's going on, it might be tricky, but if you do get what's going on, it's really like a practice exercise. Honestly, that doesn't mean it's easy, but it's more straightforward than homework 2. You still probably should do homework 2 or try it before you do homework 3. But honestly, if you're all stuck in the middle of homework 2, maybe, despite what the instructions say, maybe just take a break and look at homework 3. Here we go. I'm going to start explicitly going over homework 2 now, which we never have done yet. Or maybe we start. Oh, there goes my board. Oh, and there comes Nicholas. Hold on. I'll put the board back in a second. I'm going to start explicitly going through homework 2. Maybe we have done the first. You know what? In the chat, let me get the board back going. I want to go to homework 2 now. Maybe we've actually done already the first exercise, and maybe you can tell me that in the chat if we might have already done the first exercise. Oh, good morning. Good morning. Thank you. Awesome. Maybe tell me, I don't mean specifically just Nicholas, anybody tell me in the chat if we've already done the exercise 1 of homework 2. That would be good to know, so we can move on. But I'm going to start going over homework 2 explicitly. Again, what's now been posted is homework 3. So please get to, and yes, you still can hand in homework 2. You still can hand in revisions on homework 1. Hopefully people are seeing that they're getting more and more points as they do revisions, whatever. Once you get up, if you get up to like 33 out of 35 points, then I'm saying 33 out of 35 and giving you a critique somewhere in there of like what's missing or what could be done to make it perfect. But so that and you still can, but I wouldn't kill yourself over that. I'm not sure that it's worth it. I just want you to know, whatever was missing so that, for exam purposes or whatnot. But, by the time you get to a 33 out of 35 or 23 out of 25 or whatever, I would, I'd put it to bed and move on. So you still can do that with homework 1 or homework 2, but we are up to homework 3 now. Again, for these people who just joined or whatever, homework 3 is shorter and more straightforward than homework 2. It really is practice. And as it says in there, usually the problem that is homework 3 usually reprinted and becomes an exam problem. So it's a good practice. But anyway, all right. So I'll try to highlight what the point of it is as we go through homework 2 right now. Yes. So good morning. Good morning. I think I said good morning to everybody. Okay. Okay. So here we go. Oh, all right. What's on the board here is there goes the board again. Good heavens to Betsy. Well, it's about to disappear. It's a delay on the problem. Well, before it disappears, as usual, what's on the board is sort of what's going on, but where we are and where we're heading. The little part in brown is the new information that we're going to get to hopefully today. But the rest of the stuff that's in black on the board here should be starting to really look familiar to y'all. And here's the key point. The key point is that, one second. Just make sure the board is still there. Hold on. Maybe. Okay, I'll direct your attention to something quick, like what's here on the board. The differential equation is on the bottom of the board. The solution or a solution in general is on the top. Granted, the little brown bit that's added is like what we have to start adding today. But you hopefully are getting to the point of recognizing that this differential equation on the bottom is the differential equation that describes harmonic oscillation, like, right? That's the math expression that describes the physical system that we have been investigating for a very long time. So that's the differential equation that describes the simple harmonic oscillator. The solution is the cosine expression up above. So what we're saying is whenever we have whenever we have any variable z, any measurable quantity that varies in time, that varies in a way that depends on time. So z can be anything, right? If z can be described by that differential equation, then z oscillates harmonically in time, right? Okay, that's what we're saying so far. Harmonic, oscillates in a manner that can be described by a cosine in time. But more specifically now, I'm just going to remind you or say again, that differential equation at the bottom says that the second time derivative of z is directly proportional to the negative of z, right? That I'm just putting it in a different way in English now. I'm saying the differential equation says that the second time derivative of the quantity z is directly proportional to the negative of z, right? i.e., the second time derivative equals negative times some constant times z. The constant is what we are calling omega squared. Right now, okay, please bear with, I've said this a million different ways, but I'm trying to say it a different way. Now, I'm saying the differential equation says that the second time derivative of z is equal to a negative times some constant times z. The constant is what we are calling omega squared. You might very well say, either consciously or unconsciously, you might say, wait, why are they calling it omega squared? That's like so annoying and confusing. Like, why don't they just call it K for constant? Or why don't they just call it C for constant? Or if they insist on these Greek letters, like, why do they call it omega as it means constant? Like, I can almost get what Yaveram is saying if you would just call the constant just like some simple letter. Why is he calling the constant omega squared? And please listen to me. That is what I'm doing. That is what I'm doing. I'm saying the whole constant is called omega squared. Now, why am I calling it omega squared? Like, and please notice, I'm calling the constant omega squared. Oh, there goes my board again, of course. Oh, and here's Jamalet. I'm sorry. Wait, okay, Jamalet and board. Enter. Okay, well, okay. Well, I'm calling omega squared. I'm saying that the constant, and what do I mean, the constant? The constant in the differential equation, the constant that's being multiplied by z and also being multiplied by -1, or z being any variable we're talking about, like, right? Why am I calling the constant omega squared? I will tell you why. I'm calling it something squared. I don't have to. I could call whatever I want. That is true. I could call whatever I want. But there's the advantages to calling it omega squared are twofold. One, it emphasizes then that it's a positive number. Okay, like omega in principle could be any number, maybe in principle could be any number, but by squaring it, I'm ensuring that it's a positive number. So therefore, the negative sign out in front, like, is explicit and clear and meaningful. Like omega squared is a positive number. So then the negative means that the whole thing is in the opposite direction from Z. The whole thing restores Z back to 0. What is Z again? Z is any dependent variable at all. Like lately, what it's meant is X. It's meant the position of a mass on a spring, right? Like lately, we've been using the variable X, but I'm now calling it Z to cover the idea that position of a mass on a spring was a central example, the very first example that we're looking at that actually symbolizes or typifies or represents any kind of system at all that behaves this way, including, for example, pendulums, like you did in lab number 2, right? We spent all this time studying mass on spring systems, as boring as that may very well seem. Like, of course, I understand, like we've been a month on a freaking mass going back and forth on a spring. But what we're trying to really develop is we're trying to say, once we really understand how a mass goes back and forth on a spring, we realize that anything in life that acts like a mass on a spring acts exactly like a mass on a spring. We're using mass on a spring as the physical representation of any system in the world from now on that oscillates harmonically, whether that be a pendulum on a string or a current in a capacitor circuit, or temperature in a system, as is the case in homework 3, right? We're saying from now on, anything that's described by the same differential equation that describes the mass on the spring will then behave in all respects the way that a mass on a spring does. And a mass on a spring is the simplest, or at least easiest to picture, version of this whole topic of harmonic oscillation. Okay, so from now on, I often will use the variable Z to represent whatever quantity it is that we think is going back and forth, going back and forth, going back and forth. Okay, so now the differential equation in general, we're saying if you have any variable Z, such as in homework 3, the temperature, if you have any variable Z, oh, excuse me, this is my mirror, sorry. If you have any variable Z that can be described by that differential equation that says the second time derivative of Z is equal to a negative times a constant times Z itself, right? Well, first, the constant we're calling omega squared, number 1, to ensure that once it's squared, it's positive, so that that negative sign is doing what we think it's doing, which is to literally mean opposite direction of Z. It means that if Z stands for position of a mass on a spring, then when Z is positive and to the right of 0, to the right of the equilibrium position, then this acceleration, this change in time will pull to the left toward 0. But if Z were on the left, then this whole direction will be opposite to that. It'll pull it to the right. The negative sign means restoring to equilibrium always, right? And we can see that the negative literally negates the direction of Z as long as the omega squared itself, the constant, is always positive. So number 1, we're calling it squared to ensure or remind ourselves that it's definitely positive, whatever's in that parentheses. But number 2, the biggest point of all, and then I will move on, I think, we call it omega squared because what we're really saying, and this is the key, what I'm about to say is the key insight for all of homework 3. If you get what I'm about to say, then homework 3 will be like a break, will be a refreshing break from homework 2 and 1. Honestly, it will, if you get what I'm about to say, which is this, which is that, well, you need my board to see what I'm saying, which is this, hang on, coming, board coming. Right, which is this. Okay, like it, look at the, I'm going up the board. I'm reading up the board. If you look at that differential equation at the bottom, any variable that's described by that differential equation will necessarily oscillate harmonically, the value of the variable will fluctuate up and down in the manner of a cosine function with an angular frequency, with a rate, with a cycling rate that is necessarily the square root of whatever that constant in parentheses is. Like the reason, let me see if I can do this. The reason we're intentionally calling that constant omega squared, again, we could call it whatever, sure, we could call it C or B or something, but we call it omega squared with the benefit of hindsight, because what we're saying is if a variable can be described, if the second time derivative of a dependent variable is directly proportional to the variable itself with a negative sign, then the variable will oscillate cosinusoidally at a rate that is necessarily the square root of that constant of proportionality. The angular frequency, the rate at which this thing cycles back and forth, is necessarily the square root of whatever that constant is in the differential equation. Like once you get that, granted, we've spent like a month building up to that insight. It's not an easy insight to develop, but once you have the insight, it makes life really easy. In short, if the homework says that the temp, which it does, if homework 3, so anybody who's listening right now, I'm about to basically give away homework 3, okay? If homework 3 says that the temperature is described by a differential equation, if capital D stands for temperature, as in like degrees Celsius or whatever, if capital D stands for temperature and D2D dt squared equals negative, I don't know, 121D, I believe, I don't remember what the number is in the homework, but say it's negative 121D, right? That means that the second time derivative of the temperature is equal to negative times a constant times D itself. Then D itself oscillates cosinusoidally at an angular frequency of square root of 121 radians per second, like literally 11 radians per second. I don't remember if the actual number in the homework is 121, but I think it is. I'm telling you the point of this whole thing is that a system that's described by that differential equation will oscillate cosinusoidally at an angular frequency of the square root of whatever the constant is in the differential equation. So we call the constant omega squared to remind ourselves, yeah, it's the square of whatever the angular frequency is. All right, that either helped or it didn't, but that's the summary of where we are right now. Now what I'm going to do is I'm going to start walking through homework 2, hopefully, and hopefully that will help you too in a different, it'll be maybe more straightforward for some of you. All right, I'm going to change the view on the screen, but stop me in the chat if excuse me. So I'm just going to start walking through. I might go a little fast at first because I feel like now this is getting repetitive for some people in the room, but I'm going to start walking through homework number 2. Oh, and someone's here. Oh, hello. Okay. And pardon me for a minute because I'm also going to change so I can see the homework 2. I'll try at first. Okay, I'm going to assume I have not walked through this yet. Please. Oh, sorry. Okay. Wait, I'm trying to get. So I'm going to try to walk through. If I can just get. Where did it go? Come on, come on. Okay, I'm going to try to walk through homework 2 math methods. Maybe at first I'll do a full solution for the first one to be clear, but then from then on I'm just going to sort of bang through answers, if that makes sense. And I'm looking at 3 screens at once, so please, if there's any question or any issue, at least for the moment, shout out, please, or something, because I can't see the chat just yet. Right at the moment, I'm looking at the sheet. But okay, so this is math methods, homework number 2. But also, if I've already done some of this and I'm wasting your time, please tell me. All right. Okay. So first question, this is the first part of the sheet math method, derivatives get, I want to say, so it asks for derivatives. It's about to ask for derivatives, but I'm going to do at least once. I want to do the 5-step method to make it clear to all of you, like, especially if an exam is coming up, perhaps we really want to know this 5-step method. So step 1 is supposed to be diagram and fact pattern, right? Well, here's the facts. The given is x equals a cosine omega t. Now, there's no diagram in the original sheet, but that's all the more reason that we should provide at least one diagram, maybe not for every one of these repetitive problems, but at least at first, we should provide some kind of diagram. And I know I'm commented on that in many of your homeworks. What kind of diagram could we provide? Well, it's a cosine function. Let's provide a cosine graph. Now, I don't mean like a point-by-point scatter plot, but let's label our axes and let's label a key point or two and give the shape of the graph to make it clear. So this is t measured in seconds on that axis. This is this is x measured in meters on that axis. It's important to see what's the dependent variable, what's the independent variable. It's a cosine function, so it's like that's the shape, right? And it doesn't start at 0, 0. Where does it start? Well, according to this, wait, I'm looking at, okay, I think I've got, oh, something in the chat. I'm sorry, let me see. Oh, no problem, no problem. Got it, thank you. Like this is what I would consider to be a graph in physics. Labels axes, otherwise nothing is meaningful. I label my axes, ideally provide units because it's a science class. I label some key points, such as the y-intercept. What is the y-intercept? Well, it's not 0, right? Because it's cosine. If it were sine, it might be 0. It's cosine. What's the y-intercept? Well, when t equals 0, what is x? According to this function, x is called a, right? I mean, as in amplitude. So that point is 0, a, like, right? So this is a fairly well-labeled graph already. I mean, you can, and there's one other thing I can put in it, just to make it clear, to get you used to, like, because there's one other, remember the point of a good diagram is to label every single variable or constant that's going to be used in the math that you're using to solve the problem. So the point of a diagram is to define, it's to use your labels to define all terms. That's really the point of a diagram, or a big point of a diagram, is to define all terms. So the one term that hasn't been made clear, I mean, there's an x in here, this makes clear to me that t is the independent variable, x is the dependent variable, a is the initial value of x, right? I mean, a is the same thing as x naught, according to this. And how did I know that? Because I know the cosine of 0 is 1. So if I plugged in 0 for t, then 0 times omega, whatever omega is, 0 times omega is omega. So the cosine of 0 is 1. So I would get 1, but then 1 times a gives me x, right? I mean, maybe that's not clear. In other words, at t equals 0, x equals a times 1, right? According to that expression. So I'm labeling that in my diagram. Like, that's what I'm learning from that expression. And one other thing is, what's omega? Like, where do I see omega in this graph? I think it's helpful to know that what omega is. Oh, hello. Well, yeah, like the space between two peaks, the interval as measured along the x-axis between two peaks is 2 pi over omega. Omega is the number of radians we're doing per second. So the flip of that is the number of seconds per radian. Only the x-axis isn't measured in radians, it's measured in seconds, right? There's let me put it another way. There's 2 pi radians in every cycle, right? And a cycle length on this axis is measured in time units. So you could say, in other words, I'm saying omega is 2 pi over, well, let me make this explicit. There's various ways I could put this. I'm saying, if you want to see where omega is on this graph, Say it either way you want. I'm saying if right, if T, capital T, is what it's called the period, the amount of time for one full cycle, the amount of time from one peak to the next peak, or one trough to the next trough, or whatever, right? If capital T is the distance along the x-axis between those two peaks, then 2 pi over it is what we mean by omega here, and the reverse. That's what omega is. It's the number of those cycles that we're doing per second, only measured in radians. And there's 2 pi radians per every cycle. So now I have a fully labeled, I didn't mean to overtalk that, but I did. That's a fully labeled diagram. That diagram shows every term that's in my expression and helps me visualize it, hopefully. Okay, so that's the for those of you who are, like I said, you know, for full score on this whole thing, please provide a diagram. That's the one I mean, or something like it. And you don't have to do it every single time. Just now we've got it. We can refer to it later. All right, but anyway, that's the so now there's my step 1 diagram and fact pattern. Okay, so then step 2, what is the question? Oh, sorry, what is the question? And please make this explicit. Don't have your reader figure out what the question is. You can distill it, you can summarize it as simply as you can, but make the question explicit. So the question explicitly is, I believe, sorry, now I'm going to switch screens again, sorry. Yeah. The question explicitly is, what is the first derivative of that expression of x equals a cosine omega t, right? That's step 2. So now step 3, jjP, what are the general principles and definitions used to get a derivative of this cosine expression? Here's what I would say are the general definitions and principles. And again, I'm not going to drag this whole thing out for every single exercise, but just to make it clear, like what I'd be looking for on an exam or whatever. And we're trying to get the derivative, and I'll write it again just so we can see. Like the given was x equals a cosine omega t, right? Well, what are the general definitions and principles? I think the general definitions and principles are, one, that if, well, here, we'll say in general, if y equals cosine of x, then I think dy dx equals negative sine of x, right? Now notice, please bear with me. I just switched variables, right? What we're given here is an expression x as a function of t. Now I just switched and talked about x and y because I'm saying my general point, my general thing, like from a math class, is that in general, if you have y is some cosine of x, then the derivative of y with respect to x is negative sine of x. You see what I'm saying? That's like the general. In other words, that's a truth that is true even before this problem began, right? It was just true. But I mean, it's hopefully it's on the topic of this problem, but it's true even before this problem began. Also, similarly, so that's a jjP, right? Also, similarly, in general, if y equals some function of x and also if z is some function of y, then I think dz dz dx equals dz dy times dy dx. We said this 2 classes ago or something. This is a reminder, or my way of putting the chain rule, right? This is true in general. So we have 2 statements. We have how to take a trigonometric derivative, or we have how to take a derivative of a cosine function, and we have how to take the derivative of a function within a function. So that was jjP, step 3. Now I'm going to apply those general truths to this particular problem. Right, so I go to the next page. Step 4, particular application and work. Now I'll apply it particularly to this problem. So here, here, I'll say this here, y equals omega t and x equals a cosine of y. You see what I'm saying? I'm like substituting in the, and maybe you think I'm making, it doesn't matter what I'm just showing, like, here we have a function, y equals omega times t. Then we have a function of that, x equals a cosine of that function. So the derivative of x with respect to t would equal would equal dx dy times dy dt, right? And please, x, y, and t are any variables. Like in this case, t is the independent variable, y is a dependent on that, and then x is dependent on that. Right? I'm just setting up a pattern here. So dx dy is negative a cosine, negative a sine of y, and then times the derivative of y with respect to t. That means all times omega, right? So it's negative a omega sine. Now, what is y? Y is omega t. I'm dragging this out. Those of you who think this is obvious, good. I understand you think it's obvious, but if it's obvious, you can explain it, right? This is how you explain it. Okay, so that's the first derivative. So I just did out the work. So now that's my answer. My answer for the very first question. So I circle it, and please do that in your homework. That's something I know some of you did really nice, like all this work and stuff, but then, and you even showed me the question. Maybe you showed me a diagram, although often not. And then you get to the answer and you just write the answer and it looks the same as all the other things. And then you move on. It's really important to show that you know when you've landed on the answer. It's not just to make my life easy, although that's a big part of it, but it's also like, just like you want to show that you know what the question is, you want to show when you know that you've answered it. I can't put it more explicitly than that. So here's my answer, and I've just circled it. So that's step 5. Final answer circled. Step 5. Final answer circled. Okay, so I'm done, which is that first exercise. Now, again, I'm going to try to speed up a little bit now. Like, I'm not going to necessarily drag all of this out for everyone now, but that's how you do it, I think. So that's answer to number 1. And let me just look in the chat, see if there's any questions. I'll pause if there's. Are we cool? Wait. Oh, let me just. I know that was like long, maybe. But can I get a thumbs up if that was clear? Do we all know where I am and what I just answered? Thank you, Olsmail. All right. Thank you, Sophia. I appreciate it. All right. That'll be good enough for me right now. It's a little scary. That's only 2 people. Oh, thank you, Brooke. Thank you. Oh, now we're going. Thank you, Amy. Thank you, Sophia. Thank you, Jim. I'm like, oh, and he even clapped. All right. Awesome. All right. I'll take that as a something. Excellent. All right. So I'm going to move on. Now I'm going to go a little faster now. Look, I don't mean I'm going to talk faster. Hopefully not. I'm talking, but I mean, I'm not going to like do out all the steps now. I'm going to assume that you can replicate this method of doing the steps. I'm going to do more of a skeleton from here on in. So I'll even make that clear. Okay, so we're now up to 2. So it asked. Okay, so then 2 asked, and we're still talking about the same function now. We're still talking about x equals a cosine omega t, but now it's asking what is d2x dt squared, right? So it's asking the second derivative now. So I think the thing to do is just take the first. All right, so sorry, hold on. It's asking to take the derivative of the thing we just got a minute ago. The thing we just got a minute ago was this. Oh, hopefully, did I? Yeah. Okay, so that's what we just got a second ago. So or a minute ago. So now we're asking for this. So we're asking to do the same process. Take the derivative again of the above. Here, if I were doing it, I'm not going to write, if you were doing the step 3 GDP, I would now write if y equals sine of x, then dy dx equals cosine of x, or put in the negative signs you want. But the key point now, I guess I will write that one. I'm not going to write the chain rule again and stuff, but I will write like note. If y equals sine of x, then dy dx equals cosine of x. Put another way, if y equals negative sine of x, then dy dx equals negative cosine of x. What I'm trying to emphasize here, that does confuse people sometimes, is we don't get rid of the negative sign right now, right? Like when we went from cosine to sine, we introduced a negative sign. But when we go from sine to cosine, we do not introduce another negative sign. So we don't cancel out the old negative sign. That's like actually really important. The negative sign stays with us when we take this second derivative. If we took another derivative, it would go away. But we're literally landing on the second derivative here. So d2, so back to the problem, d2x dt squared here equals negative a omega cosine omega t. But the chain rule does bring out omega again, right? So that does happen again, that the omega comes out again. Therefore, it's negative a omega squared cosine of omega t, right? Please stop me if you don't. And it's convenient. That's the answer. And if you circled that, great. You can circle that. But I'm even going to go a step further because I'm anticipating where all this is going. And I'm going to write it like this. Right? I'm just switching. I mean, multiplication is commutative. So I'm just switching the order of the constants to keep things neat and tidy. I'm switching the omega squared. Notice omega squared is just a constant. It's just a constant. It's a package unto itself. I switched it with the a because I can do that with multiplication. And this is my final answer. Now, why did I write it like that? Because I believe the next question cares. Yeah, we then go to the next question. The next question is x equal a? Now, we've talked about this in class. I'm going to hopefully do this fast. Is this a solution to the differential equation right? That's the question. So look, well, I'm going to the next board, sorry. Right. So we're asking whether that cosine expression satisfies a particular differential equation. And the differential equation presented here is the one that we've been working with for weeks. It's the one that describes harmonic oscillation, right? So the question is, we're checking the solution like we've been talking about in class. So I'm just going to go to the next page. So, okay, I'll repeat up. Does x equals a cosine omega t solve d2x? Sometimes I put the parentheses, sometimes I don't. That's a question, right? Well, we just figured out that d2x, we just took two derivatives of x and found out that when we take two derivatives of x, we get this. But this is equal, like that whole thing in blue is what we're testing out as x, right? So apparently I mean, it seems so obvious once you write it down, but the reason I've taken so long and the reason I showed you an example the other day where it doesn't work out is that, yes, once you recognize that A cosine omega t is X, then it's easy if you recognize that. But this is why you have to practice on your own. Once I recognize, and in other words, the key thing is I had to rearrange, I had to switch the order of the omega squared and the A to even see what's going on here. Once I switch the order of the omega squared and the A, then I see that when I took two derivatives of X, I got back X times omega squared times a negative sign. So yes, that particular choice of X did work. Not all choices of X will, but that one did. That one doesn't work for all differential equations, but it works for this differential equation, okay? But it's easier to see than to do on your own. But the answer is yes. And therefore, what that really means is if we knew that that differential equation is true, and that differential equation is just Hooke's law written in math terms, if we know that that differential equation is true, then we know that from here on in we can predict where the oscillator will be at any moment of time with this cosine expression. Like that's what we're saying here. But so the answer is yes. And the answer, as to the question why? Because the second derivative was indeed directly proportional. The second derivative, this is illegible, but the second derivative of, the sheet asks why or why not. The answer to why is because the second derivative of X was indeed directly proportional to X itself. That's what we're trying to show here, and that's the case. Okay, I'm going to move on, but you could stop. Well, let me look in the chat. We're good. We're good. Okay, we seem to be good. Stop me if we're not good. I'm going to try to go. All right, so that was B. Now, again, hopefully you're with me that we're on homework 2. That was 1A and B. Now I'm going to C. C, now the question moves a little faster. Now it just gets straight to the chase. Instead of walking, what we're trying to show you here is the way to test possible solutions to differential equations is you take derivatives. So we walked you through that for the first exercise. Now in the third exercise, it doesn't even remind you how to do that. It just asks the question. In number C, it just says, is X equals A cosine of 5t? Hello. A solution to d2x dt squared equals negative 3x. Now, again, here, if I were doing the homework, I would either draw a new cosine graph with a new omega or refer to the above graph. But like, we're in a different cosine function now. Either refer to the above diagram and tell me how to adjust my thinking, or give me a new diagram, but let's not lose sight of the importance of visualizing these things. But okay, but here's the question. Is X equals A cosine 5t a solution to d2x dt squared equals negative 3x? Now, here, what we're trying to do here is now we're trying to get a little more refined. We're trying to say, hopefully you're getting used to the idea that the solution, hopefully you're getting used to the differential equation that we're looking at. Hopefully you're beginning to see that cosine provides a solution to that differential equation. But now we're trying to be really clear and say, okay, but let's not jump the gun, or let's not jump off into the wild blue. Not all cosines are going to solve all harmonic oscillator equations. Like, let's be careful. Here's our potential solution right here. Right? Here's our potential, our conjectured solution is right here. So what should we do to test it? We should take two derivatives, just like we did before. So I will do that more quickly now. I'm going to take two derivatives of that and see what happens, right? Because it's looking pretty good. I mean, it's got a cosine, it's got a number before the t, it's got an a. It looks like it really could be a solution to the thing, to the differential equation. So here we go. So I'll test. And again, well, yeah, so I'm going to test. Well, dx dt equals negative 5. Oh yeah, okay, I'll do it in step by step. Negative 5a sine 5t, right? I just did what I did before. I turned the cosine into a negative sign and I brought the 5 out from chain rule. I did it all in one step, but that's the first derivative. And then I do the second derivative, same thing as before. I bring out the 5 again, so I get negative 25a, but now the sine turns back to a cosine. So here we go, right? So that's the second derivative. Okay. And I can note, and I'm trying to write it in the helpful order that I did before. I'm putting the omega squared out in front and all that. So now I notice again, oh, look at this. Okay, this part here, is there something? That part there is x, right? I mean, that's what I'm testing. X equals a cosine 5t. So what I got was, this time I got d2. So I did get, notice, I did get that when I took the two derivatives of this cosine function, I got back a negative times a constant times the cosine function. Of course, like that's why we like cosines. Whenever you take two derivatives of cosines, you do get a cosine times a negative. So that's the good news. So it's looking good. But if I'm really careful, I get well, I'm sorry. Now look, I did the same process as the last problem, but just to be clear, now when I take two derivatives here, I get negative 25 times the original function, but I'm supposed to get negative 3 times the original function, right? So the answer to this one, I mean, and I think most people whose homework I've seen, and you can still hand it in, but most people whose homework I've seen did realize this is not the same thing. It's close, but no cigar, right? So the answer to this one is like, no. What was that problem? Sorry, let's move back. No, x equals a cosine 5t is not a solution to d2x dt squared equals negative 3x, because, simply put, because 25 does not equal 3. Or put in more physical terms, in physical terms, what we're saying is x equals a cosine 5t is a harmonic oscillator. It is. And d2x dt squared equals negative 3x is a harmonic oscillator. It is. But these are two different harmonic oscillators. They have two different angular frequencies. It's not the same mass spring system. They're both mass spring systems if you like, but they're going at different rates, i.e., it's a different spring stiffness and or a different mass. Do you follow me? And where did I get that from? Because I think omega equals square root of k over m, but that's from last class. But okay, so it's not a solution. It's got the right form, it's got the right character, but it does not have the right details. Okay, so that's that for that one. Stop me. I'm gonna. Okay, and I'm sort of intentionally not so. So are we okay? I'm gonna keep going. I'm just trying to make tracks here. I'm not trying to rush your thinking. I am intentionally today sort of just like not asking you to do these. I'm just because you've done them for. But are we okay? Can I move on? I mean, could I get a thumbs up? Okay, thank you, Jalen. That's good enough for me. Okay, one person. That's good. Thank you, Sarah. That's good enough for me. All right, I'm moving on. Then thank you, Stephen. Okay, and thank you, Amy. And I love this part when everybody else is like, "Oh, wait, what? No, I'm just kidding." No, okay, thank you, Abdel. Thank you, Nicholas. Thank you, Sophia. All right, so I'm moving on to the next one. Wait, but I'm changing the view. Okay. So I'm changing. Okay, so now we're going. We're almost at, okay, the next one I'm going to go, the next one I'm going to hopefully do the next one is repetitive. It's, well, the next one is now we're saying given x equals a cosine. Hello. And I don't know why the Roman numerals skipped here, but okay. So now same deal again, almost repetitive, right? But now we're calling that constant, instead of calling it a number, like the constant right before the t, that rate, instead of calling it a number like 5 or 3, and instead of calling it like omega, the Greek letter, we're calling it a combination of English letters, square root of k over m. Hopefully some of you already understand why we're doing that, but now it's to relate it back to our original thing that started all this madness with this, which is a mass on a stiff spring, right? But I'm just doing math here. It's asking me to take the derivative. So I take the derivative dx dt equals negative square root of k over m times a sine of negative square root k over m t, right? It's the same thing as before, only squared. It's also trying to get used to the fact that like a package of constants is a constant, if you know what I'm saying. Like k is a constant, m is a constant. Therefore, the square root of one of them over the other is a constant. All right, so I took the first derivative. Stop me if you don't like it. I'm serious about that. Again, the faster I go does not mean you should not stop me. It means as long as you don't, I'm going to go this fast or this whatever. Anyway, so now I take another derivative. So I do the derivative again, chain rule again, the square root of k over m comes out again. So now I get so now the square root times the square root is a square. What? You know what I'm saying. So I get negative k over m times a times cosine of negative k over m. That's the second derivative. So this was the first. This is the second. Go to the next page. Oh, so it didn't even ask, but you see why I just did that? So this is just, again, to reinforce or show what we've now been saying in the class, that if you have Hooke's law, this is Hooke's law right here, just in mathematical terms, right? If you have Hooke's law, the solution to it is this, right? Or put another way, in fact, well, yeah, put another way. It's saying what I showed either last Monday or last Wednesday on the video, I can't remember. It's saying, look, if you've got the Hooke's law differential equation, the solution to it is x equals a cosine omega t, as long as we understand that omega stands for the square root of k over m. This also goes back to what I was saying at the beginning of today's class. We have an oscillator that is oscillating at an angular frequency, which is square root of the constant in the differential equation. The constant is k over m. So we've got something oscillating at a frequency which is square root of k over m. It is oscillating at a cosine omega t as long as omega stands for square root of k over m. And I'll say one last time. Well, it won't be the last time. I'll say again. You might be thinking, wait, why does he keep going back and forth? Like, why does he sometimes call it omega and sometimes he calls it square root of k over m? Like, can't he just pick one and stop being confusing? Well, no. I mean, I could. But the reason I keep going back and forth is Square root of K over M are the original parameters provided in this system, measured for this physical system. K is the stiffness of the given spring. M is the mass of the given object on the spring, right? Those are the measurable descriptions of our physical system. What we are saying, what we're learning or figuring out is, oh my God, this system will go back and forth and go back and forth at a rate, which is the square root of those two parameters. That's a discovery. Like omega is the term we use when we're talking about the rate in radians per second of this cycling. And K over M are the original parameters of the system even before it started cycling. So we're saying as long as you know how stiff the spring is and as long as you know how heavy the mass is, you know automatically how fast it's going to cycle back and forth. That's actually pretty heavy. I mean, pretty intense, pretty awesome. And again, we're saying the rate at which it'll go back and forth has nothing to do with A or nothing to do with X naught. It doesn't matter how you set it up. It just matters what you set up, what the stiffness is and what the mass is. It'll cycle back and forth at a certain number of radians per second. Boom, square root of K over M. And last thing, again, if you say radians per second, you have about why radians per second? What's a radian? A radian is a sixth of a cycle. End of discussion. Probably not the end of the discussion with me, but a radian is a sixth of a cycle. Technically, it's a 2π of a cycle. That's what a radian is. It's a thing that 2π of them make up a cycle. And 2π is approximately 6. So a radian is approximately a sixth of a cycle. So omega radians per second, angular frequency is just cycling rate, only instead of counting each full one cycle, we're counting each sixth of a cycle. That's it. Okay, moving on. Now we're actually, so that's it for, okay, now we've got 18 minutes left. This is exactly where I want to get to. This is actually, okay, so we're going to do F now. F is actually a little bit interesting. It actually pushes the material forward. So the others were ideally practice whatever I just said, or review or refresh or help. Now we're going to push the material a little bit forward. F says, it gives a new possible solution. It says, okay, how about this? And again, remember, we're trying to solve the differential equation for harmonic oscillation. We're taking these guesses and we're testing these conjectures and testing them to see if they work. This homework right now is not building up the guesses, it's just plopping guesses on your piece of paper and saying, try this, try this, try this, right? So now we're trying a new one. It's saying, how about this? It's saying, given X equals A cosine omega t plus 3.5. Okay, now 3.5, there's a random number being stuck into parentheses. Let me tell you, first of all, yes, it's a random number. It's literally meant to represent any random number. It could have been 1 point. There's nothing significant about 3.5, only that it's a number, a constant. It's a randomly chosen constant value, 3.5, right? But I'm going to say this with 16 minutes left. 3.5 is a randomly chosen constant value that must necessarily be measured. I almost want to ask you. Yeah, I'm going to do it. I'm going to do it. If you just look at where it is in the parentheses, it's being added to omega t. It's in the parentheses, and then we take a cosine of the whole package. So whatever 3.5 is, it must, and I'm asking you, this is the one question I'm going to ask in today's class. What units must 3.5 be measured in for any of this to make sense or be self-consistent? What units? And please put in the direct chat, in the private chat, please. But I'm going to wait until I get at least 2 answers in the private chat. What units must the 3.5 be measured in for any of this to make sense? And you know these units. I mean, I'll even give you a hint. They're not technically even units. They look like units, but they're not. It's a word for like a place. But what is the 3.5 measured in? 3.5 watts. So I'm going to repeat the question, and I'm not going to go until I get two things in the direct chat, whether they're right or wrong, or even if they're, I don't understand the question. I'm asking that 3.5 right there, just for that expression even to make sense. Even if you're, okay, fair enough. Wait, thank you for the chat. Okay, that's fair. Thank you, chat person. Someone in the chat just said like they are listening, they're with me, but they don't know the answer. That's fine. That counts as one thing in the chat. I'm down with that. I appreciate the honesty. I will repeat the question, but I'm saying 3.5 must be met. It's 3.5 watts is my question. Now, a big hint is it's being added to omega t. What units are omega t measured in? Not omega. Well, if you know omega, then those units are being measured by whatever t is in. And we designed omega so that those units would multiply by the t units, and then we could take a cosine of them, right? 3.5 has got to be in the same units as omega t so that we can take a cosine of it. So one person has at least said in the chat that like they're so close. Oh my God, so close. And it's the same person in the chat. I totally appreciate it. You have exactly right. It's even simpler than what you're saying. Wait, okay. Now there's two people in the chat. So I'm going to, so thank you people in the chat. Okay. I will, but thank you. And please submit those for points. I think every single point you've submitted for, you've gotten so far. I think you two. So get more. But what I'm going to say that, so one person said, well, I won't tell you what they said, but the 3.5, I'll tell everybody. And then I want the two people in the chat, once I say this, to tell me if it makes sense to them, like in the direct chat. But I'm going to say to everybody, the 3.5 has to be measured. It has to be measured in radians. Because omega t is measured in radians, and you can only add radians to radians. How do I know the omega t is measured in radians? Because you can only take a cosine of radians. Remember, omega is radians per second. Radians per second was designed to cancel out with the seconds to be left with radians. Anything in the parentheses has to be measured in radians. Now, and I do understand what the, oh, okay, cool. Thank you. That's one direct person, other person, because you're going to get like 50 points if you think about it. You could, both of you in the chat, you could submit for putting in the chat, you could submit for closing a conversational loop, and you can submit for a not exactly correct answer, although I totally understand your thinking, both of you. And again, like everybody else isn't doing, like other person, do you see what I'm saying? That it's radians. Like you can't take the cosine of anything but radians. So anything in the parentheses has to be a bunch of radians. Well, okay, at least one person's with me. But yes, other person who did go in the direct, well, wait, actually, I'm going to, wait, you've got, I can't resist. Hold on one second. I'm going to keep going. I am. But all of you, you should stop me if you are not with me. I know I've been talking a lot this period. Okay, but I'm going to move. So the 3.5, whatever it is, it stands for something that must be measured in radians. But now I'm going to take the derivative of the question in the homework was can you take the derivative of this? Because we're testing it again. So it says, what's the derivative of this new, more complicated thing? Well, dx dt, I got to do sine, and here, if I were doing homework, if I were you, I would write down the GDPs again, like write down chain rule, write down trigonometric derivative. But what do you get? You get negative a sine of omega t plus 3.5. Now, maybe I should have written this down, but we've got to multiply the whole thing by the derivative of what's inside the parentheses, the derivative with respect to t. The derivative of the whole express, in other words, and I should, if we had more, the whole, okay, I'm going to write this, but yeah, hold on, I'm going to write it, just make it clear to everybody, because I do feel like I'm losing people. Okay, I'm writing again. Here, the expression is a cosine omega t plus 3.5. So that's like saying y equals omega t plus 3.5 and x equals a cosine of y. Stop me if you don't understand what I'm saying, but right, going back to chain rule, I'm saying the inner function is omega t plus 3.5. I'll even be more clear. I'll try to be more clear. I'm saying y as a function of t is that, and x as a function of y is that, right? So now chain rule says do the derivative of the outside times the derivative of the inside. So the derivative of the inside, if we had a little more time, I would be asking you this right now, but the derivative of the inside, like derivative of y with respect to t, you know, yeah, I've got to ask. Anybody, could be one of those two last people, but what if y of t is omega t plus 3.5? 3.5 is a number. It's a constant number, okay? If y of t is omega t plus 3.5, what is dy dt? Somebody in the class, please, I'm not angry. I won't hit. I'm just, what is dy dt? What's the derivative of the inner function with respect to t? I'll just wait for one person to tell me a right or wrong answer. What is the derivative of y with respect to t? Oh boy, people. Okay, thank you very much. Okay, that's the outer. Person in the direct chat is rocking this class. Thank you, person in the direct chat. What you did was the outer derivative. I want the inner one. Like you did the derivative of the, I want the derivative of, so, okay, you're with me. You're totally with me, direct chat person. And there's only one of you right now, so you know who I'm talking to. But you did the outer thing. I'm talking about the inner thing. So I'm just going to say to everybody in the interest of time that what I'm looking for here is omega. The derivative of omega t plus 3.5 is just omega. What I'm trying to say to everybody, and by the way, if you're just like spacing out, oh, okay, cool. Okay, cool. Okay, cool. But thank you both, direct chat people. I totally see it. No, good. Like two people are with me. And look, the rest of you, honestly, we only have 8 minutes left. There's one of two things happening right now. Either this material is like actually over our heads or it's like confusing us, which I need to know if that's the case. That's not a bad thing, but I need to know, or everybody's just spacing out. Because I want to make clear the derivative of the inner function here of omega t plus 3.5 is the same as what it would be if the inner function were just omega t. What I'm saying is the derivative of the inner function did not change at all. Because technically, in other words, the derivative of the inner function is technically omega plus 0. Because the derivative of 3.5 is 0. It's like, what's the derivative? If y equals mx plus b, the derivative of the whole thing is just m. You follow me? It's like m plus 0. Well, hopefully you follow me. Therefore, from chain rule, what I'm saying is dx dt, and I'm going to wrap this up in a moment, but I want, this is important. So I'm almost hoping in a way that everybody's just spacing out because we do need to get this. This is about to be a new thing. Dx dt will equal negative a sine of the whole inner, which is what two people in the chat told me. So they are with me. Thank you. Like it's the derivative of the inner whole thing, omega t plus 3.5. But all of that times the derivative of the inner. The derivative of the inner is just omega, just like it was before. So now we're going to move on. We've got 7 minutes, right? I'm saying the omega came out. Nothing else came out. The 3.5 did not come out. The 3.5 stayed in the parentheses, but it didn't multiply out the whole function. So now if I do the second derivative, which is the second derivative is, this is F4. Sorry, I'm on F4 now, just so you know. Sorry, this is F4. I don't know why it's called 4, but it is. So d2x dt squared now equals negative a. Now that omega comes out again, so it's omega squared cosine of omega t plus 3.5. That's the that's the second derivative of x with respect to t. Again, I'm very proud and pleased with the two people that were in the direct chat, just saying. That's the second derivative. So now g, so that's the answer to f. Now here's this is important. If you look at g asks, is x equals a cosine omega t plus 3.5 a solution to d2x dt squared equals negative omega squared x? The answer to this is yes, it is. Okay, this is, we got 4 minutes. First of all, I'm saying the answer is yes to G. The answer is yes. That this new function that we just developed, that we just tried, that we haven't seen before, this function has an extra detail in it, the 3.5. That 3.5 did not change the derivative. It didn't come out and multiply. It didn't change. Yeah, it didn't change the derivatives. So the second derivative, this. Like, here's that inner function, x. So the second derivative of x was just negative times omega squared times x itself. Even though we stuck a 3.5 in the x, it changed the x, but it was just sitting there in both of the derivatives of x and it didn't come out. So apparently, when we've been saying so far that the cosine solution, we've been saying so what I'm saying is this. Okay. With 2 minutes left, I'm saying this. We've been saying x equals a cosine omega t, and you could also say x equals x naught cosine omega t. It now turns out, really, every time we've said omega t, what we were really thinking without realizing it was omega t plus 0. And what we're just shown is that actually we could stick an extra number. The 0 doesn't have to be a 0. We could say omega t plus any extra number as long as that number is measured in radians, and it still works as a solution. So from here on, so it turns out that x equals a cosine omega t was not the solution, it was a solution. A more general way of putting the solution to the harmonic oscillator is x equals a cosine omega t plus phi. That's a Greek letter lowercase phi, where phi can stand for any constant measured in radians. Phi is like a head, and you might want to write this. It's called, I'm not going to write it, the pen is down, but phi is called a phase constant. You can stick a phase constant in there, which refers to some number of radians, any kind of head start or delay in the cycle. In other words, you can give your oscillator a head start of a certain number of radians, a certain number of cycle 6, or a delay of a certain number of cycle 6, and it still will be a harmonic oscillator. So the more general solution to the harmonic oscillator is a cosine omega t plus phi, where phi is called a phase constant. It is any constant, and you could see it could be added or subtracted, any constant term measured in radians. And that constant term measured in radians represents a delay or a head start in cycle 6. Okay, good job, everybody. I think certainly 2 people. Okay, yes, good. Oh, yes, have a good day. Have a good day. Thank you very much. Have a good day. Yes, have a good day. Awesome. Thank you.
Have
Have
a
a
good
great
day.
day, Professor Yerbaum.
Thank you. Thank you. You too. Great. Have a good day. Bye. 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 That's funny. Okay. Okay. Bye.